Excellent. So we're ready then to continue with our next talk, and we are excited to have here Franca Hoffmann from CALTECH, who will talk about consensus-based optimization and something.
Thank you. I'm Carmen, and I'm requested the Alan-Turing Institute. I think most people have seen there. Yes, we won't talk about diffusion models directly. Talk about optimization, and then also a little bit of some triangle that will connect to a lot of functions that we also talk about. As you can tell, we talk about this here since I've done my undergraduate and also my PhD in the UK, also in London. So it's really exciting to be back to this place and also reconnect with people here. It's
Is that good? Oh, okay. All right. I feel like on a rock concert. Okay, so this is what I will talk about today is mainly these two papers, but I also want to give you a bit of an overview actually on consensus-based optimization in general and also consensus-based sampling. But these two papers are in collaboration with these four people. So Jose Carrillo, who is at University of Oxford and was my PhD advisor, and Andrew Stewart, who's also here, and I'm sure many of you know. And then Urban Reyes from INRIA, and Nico was actually a master's student with me when I was at University of Bonn. And so the second paper came out of his master thesis in the end. Nico's also looking for a PhD right now. So in case you're looking for PhD students, I can highly recommend. Okay. So first of all, I want to tell you a little bit, what is consensus-based optimization? And with this group of people, I'm very interested to actually just hear who of you knows what the consensus-based optimization algorithm is. Like maybe we can just have a show of hands, like then Okay, so the suspects that I know about it, but a lot of you don't. Okay, so that's good. It's a relatively new algorithm. So the first paper stating this model was 2017. And it sits in a wider class of models, particle-based models for non-convex optimization. And then we asked the question, how can you, this is also a more general question, how can you use a certain approach that works for optimization to turn that into a sampling algorithm in a good way? And so this worked really well for this CBO approach. So I will briefly talk about that. And then if there's time, also show you some numerics and tell you about some recent software implementations of this new approach. Okay, so what's the problem that we're interested in? So we're saying optimization, right? So we have some objective function, and for now, let's say we're in RD, but of course, it can be high dimensional. And especially when you have these very high dimensional problem and non-convex optimization problem, there's a whole zoo of methods trying to get over those challenges. And here in particular, what we're thinking about is a case where, okay, so your objective is non-convex. And then also you may not have actually sort of a clear description of how the landscape of the F looks like. So you may only have black box access to zero order information of your objective, which also means that in most cases, you're not even able to differentiate it, either because it's not differentiable or because it's very computationally costly to compute gradients. And so then you would like to find derivative-free methods. And then you may also have additional constraints for your optimization that you would like to include. So that's sort of the general setting. And there's, I would say, maybe two big classes of methods that address that problem. One is stochastic gradient type methods. So for that, of course, you need gradient information, and then you use stochasticity, for instance, to get out of local minimizers. There's been a lot of work on this, and so they're very well known for their efficiency and scalability and so on, and now also have sort of very solid mathematical foundations. Another group of methods is meta-heuristics, which take ideas from other areas, sometimes biology, sometimes physics, and try to, well, design, let's say, a particle algorithm that way. And often they require much less assumptions than the methods in the first class. And so here I just put a list. You probably recognize a few of them. So this is all what I would call meta-heuristics. And in particular, the particle swarm optimization has a very strong connection to consensus-based optimization, and I will just explain that a little bit. But the challenge is that for all of these methods, it's very hard to develop rigorous theory. And in fact, there's very few sort of concrete convergence guarantees or just theoretical guarantees in general as to when these methods work in general. Okay, so one way to address this goal is to use interacting particle systems. So the idea is just you send out a swarm of particles and they explore the landscapes. They interact in some way to exchange information, and then they decide at which point they sort of collapse and say, okay, this is now the global optimum that I was looking for. I mean, here I wrote it as a sort of deterministic system, but of course you can also have the corresponding stochastic versions. And then you want all of these particles to collapse to the global minimizer, or maybe to another point, which is sort of approximately close to the global minimizer, and you can characterize how close. And so the advantage of that approach is that often these methods are parallelizable very well, and then also you can do analysis on the mean field level by looking at the corresponding mean field equations. And so this is useful in particular in inverse problems, and I guess we will hear more about the Bayesian framework this week. We have a lot of experts here, but this is a very generic sort of inverse problem where you have some parameter theta that you would like to learn. Then you have a forward map G that goes from your parameter space to your observation space, and then you assume that you have some noisy observations given. So the eta here is the noise. And we also assume that we know what the noise structure is. So actually, you know a lot of things. You know the eta, you know the G, you know you're given the Y, and you want to find the theta. But the reason why this is very difficult is because this G is not directly invertible and expensive to evaluate often, and sometimes not differentiable, especially in like, let's say weather prediction, for instance, or other very complex inverse problems that arise in sciences and engineering. All right, so when we want to find sort of either what is the most likely theta given the data or the distribution of the theta given the data, so both for parameter estimation and uncertainty quantification, the Bayesian approach is very useful. And so given some prior information of how your parameters are distributed, you can write your posterior distribution as prior times likelihoods. And then with the model that I just presented, your posterior looks like this. So you can write it as e to the minus f, where f plays the role of our objective function. So now if I want to do parameter estimation, it just corresponds to minimizing f, which would correspond to maximizing your posterior distribution. And if you're interested in uncertainty quantification, then you would like to sample from this e to the minus f. And you see that if your forward map G is linear, then this is just a Gaussian. And so this is, a problem that we know how to do, and it's quite easy. But then, of course, in applications, often this forward map is very nonlinear and complicated. Okay, so I could have put a long list here. I just picked a few sort of related approaches. And I just want to highlight a few things. So PSO that I mentioned earlier is already around since 1995. And if you go to commercially available optimization software and you want to use a particle algorithm in order to optimize your objective function, like in a non-convex setting, then this would be one of the algorithm that you would be able to select out of the box. So it's used quite widely. Now, the way that it's formulated, it's actually a second order model, and you cannot take the mean field limits. And there's currently no convergence guarantee at all. So the nice thing about consensus-based optimization is that it uses the same ideas as PSO. It has comparable or sometimes even better performance, but you're able to take a mean field limit, you're able to do analysis, you're able to prove convergence. And then, okay, there's of course Monte Carlo and MCMC and so on. But I would say you see here several ensemble common methods, right? So ensemble common inversion has become quite popular as a way of like solving inverse problems. You can also think of this as an optimization algorithm, and it's also derivative free. So in that sense, it's actually similar to consensus-based optimization. And then in 2020, we introduced ensemble common sampling, which is the idea of turning ensemble common inversion into a sampling algorithm by preventing the particle collapse. And so how we got from CBO to CBS, so from consensus-based optimization to consensus-based sampling, is a little bit a similar idea. So you prevent the particle collapse in exactly the right way. And what I'm also interested in is to understand from a little bit higher picture, all of these particle methods, how are they related, or how do they fit in the same framework, and how can the tools be translated between them? Because I would say that the family of ensemble common methods really sits sort of in the Bayesian community, or people that work a lot on inverse problems. And then the consensus-based approaches is a bit of a different community. Like especially most of the analysis has been done recently in like a PDE community. And CBO is not yet really known by practitioners. So let's say if I'm a practitioner and I want to solve an optimization problem, I would probably think of using PSO because that's what's implemented, but not of using CBO, even though the properties are actually quite nice. And then there's, I'm sure several of you are very familiar with Stein variational gradient descent, or this is a new, quite new method introduced by Aitan Tadmo and collaborators. But these two methods also use gradient information. So I think the strength of the ensemble common methods and the consensus-based approaches is that they're derivative free and you don't need to compute any gradients. Okay, so that's just for a little bit of context. So now let me tell you what CBO actually looks like. So this is the original algorithm that was first proposed in this paper in 2017. And you see that basically, okay, there's two parts, right? So you have the first part where you have a drift towards this M beta. And then you have a second part where you have noise, but the noise is scaled with the difference. So as your particles collapse to this M beta point, you also switch off the noise. So this idea of including the noise in this way really comes from simulated annealing, right? In simulated annealing, you want to add noise so that you get out of local minimizers, but then if you have too much noise, it also slows down your convergence and you jump out of the good point of the good well in the end, right? So you want to rescale this at the good rate. So what is this M beta? So this M beta is like the point that all the particles collapse to, right? And we want to choose it in a way that it approximates our global minimizer, right? And what it is just a weighted mean. So this may look, a bit complicated, but you can rewrite it as just a weighted sum of the particles. And these weights here are given by this rescaling. So here, instead of having a term of like gradient f here, which would be a gradient descent method, the objective function appears through these weights, right? They appear in this weighted mean. And the reason why that works is the Laplace method. And I will tell you in a little bit why or how. But you can also think about this physically as a sort of inverse temperature, the beta, right? So if I take the temperature to 0, I take beta to infinity, then we expect that this weighted mean is collapsing to the global minimizer, as long as we set up the initial conditions in the right way. So that's the idea. So the idea behind it is actually very simple, but very powerful. Okay, so you note that this is derivative free, like to write this down, I don't need to compute any gradients anymore. But also, in contrast to the PSO, we're able to write down a mean field limits. And actually, so far, most of the theory, all of the relevant theory, let's say, to really prove something about this are done on the PDE level. And then there is another advantage over, let's say, the vanilla Langevin or like Ornstein-Uhlenbeck process, which is that the convergence rate ends up being independent of the Hessian of the target. Okay, and so this is what I mentioned already before. The reason why this works at all is because if you compute the weighted mean of any measure, so this mu here is anything, like if I go back to the previous slide, I can define this weighted mean for any measure mu, right? So this is like as if I just multiply any measure by e to the minus beta f, and then I renormalize, right? And then I compute the mean of this renormalized measure. So if I do that for some, choice of measure mu, then as I take beta to infinity, this weighted mean converges to the global minimum as long as the global minimum is part of the support of mu. So I need to make sure that that measure that I take has like enough support. Now, obviously, if I implement the finite particle algorithm, I would choose for the mu, the empirical measure that sits on the particles. So then, the global minima is not expected to be part of the support. But we can still show, in the large particle limit that everything works really, really well. Okay. Now, maybe some of you are very familiar with the Laplace method. I just wanted to give you some background on it so that you can see, why it works. It's a very powerful concept. So here, this is this re-rating of the measure that I described. So this is what I call the R beta. And then you want to understand how, if I take this re-weighted measure and I integrate it against test functions, how that behaves in beta. And so you can write down an expansion, and at first order in beta, or 1 over beta, you get a Gaussian, where the mean of that Gaussian is exactly your global minimizer, and then the covariance is a rescaled Hessian of the objective function evaluated at the global optimizer. And then you can also look at higher order terms in beta if you wanted to. That becomes then a bit complicated. So this measure here, sort of the first order, is what's called the Laplace approximation of your e to the minus f distribution. And this is why this works. So you're basically approximating things with a Gaussian around your global optimizer. And then if you take beta to infinity, you'll see that this guy collapses to a Dirac, sitting exactly at the global optimizer, which is what you want. Okay, so the algorithm that I just presented was the first version of it that was published in 2017. Yeah?
Sorry, can you go back to it? So here, when you do the Laplace method, right, that's in the limits. So you need the number of particles to be infinite for this stuff, or?
I mean, the Laplace, this is just for any general measure.
Yeah, but in your algorithm, you have, because you replace the measure by the empirical measure, right?
Yeah. So I will get to that. So the challenge is that all the analysis so far is on the mean field level, where you can allow yourself to assume that you have nice support everywhere and so on. So there's a gap between what's happening with the actual algorithm and then what you're able to prove on the PDE level. And that's exactly the gap that we want to close. And that's also what we're working on still. Like there's like lots of steps to sort of complete to get the full picture. But I would say the advantage is that you can start with an analysis on the PDE level and expect that your finite particles, at least for a large enough number of particles, should behave in that way. Whereas for most of the other algorithm, like the meta-heuristics approaches, you just don't have any proofs. Yeah. Also, if there are more questions, please stop me. I'm happy to, I'm quite flexible in the way how I go through my slides. So if there's discussion points, I would be very happy to divert. So since this first paper in 2017, there has really been a lot of activity. And there's many different variants that came out to address certain challenges or adapt the algorithm to specific use cases. I was trying to just give you a little bit of a summary here. But if you look at the dates, you see all of these are since 2020, most of them, and some of them like this year, last year. Okay, so one idea for using this algorithm actually for machine learning applications is that you want something where your rate of convergence is independent of the dimension. So this curse of dimensionality, right, that comes to bite you. I mean, even on the PDE level, okay, there's one question of when you approximate your PDE level with particles, you have a curse of dimensionality, right? But even when you're on the PDE level, the convergence rate that you get for the original CBO depends on the dimension. And so they came up with a very nice trick. So this is this paper by Jose Carrillo and Xijin, Leili Yuhuozhu, to actually change the noise. So they actually put different noise in the different components of the Brownian motion. The different dimensions of the Brownian motion. And that means that the convergence rate becomes independent of the dimension. If you want to know how, you can look at their papers. It's a very easy trick, but it works very well. And then you can also, when you compute your weighted mean, you have to sum over all the particles, right? And you can do mini batching there as well. And so that also has shown to be quite effective. And then there's a whole range of papers that address the question of doing constraint optimization with the CBO idea. And there's different approaches, like either, for instance, you include a soft constraint in what you're minimizing, or you project, right? That's another approach. And there are also constraint algorithms for different scenarios. So yeah, I don't think I will go into all the details of it, but I think especially this very recent paper that just came out a few months ago is quite exciting in the way how they are able to include the constraints at the same time as being able to actually prove very nice properties about how that behaves as a constraint algorithm. Then it's been extended to multi-objective optimization or also to targets with multiple modes. So the original CBO assumed that you have a unique global optimizer. So you can have many local minimums. So you can have something that is very non-convex, but you want something that has one unique global optimizer. And only in that setting, the theory works. So yeah, what if you actually do have several global optimizers and you want to make sure that you have particles in each of those wells to represent sort of the distribution of the mass? So there's several papers on that. And then you can also include momentum. You can have second order versions of CBO that allows you to accelerate the convergence a little bit and also make the bridge more towards the particles form optimization, since the original PSO is a second order method. And in fact, by now we have the complete theory connecting PSO to CBO. So what happens in PSO, I didn't put that on the slide, but I can just sort of explain to you in words. You have a global best and a local best or personal best. So the global best is saying that at each time step, you check with all the particles who's doing the best, like who has the lowest energy. And all the particles get pushed towards that global best. And then you have the personal best, which is basically to say, me as one particle, I look into my past, am I doing better now than I did in the past? And if in the past I was better, I just go back to that point. And the way that that is implemented is you're actually doing a min, right? So you're sort of at each time step, you're like, okay, this is the min, this is the best point, so this is where I'm going. And this is why you cannot take the mean field limits. But using this weighted mean is somehow a soft min. So it's a way of taking an approximate min or like a reweighted min that allows you to still look at the mean field formulation. So if you take, if you take that beta to 0, for instance, then you would have the just taking the minimum basically. And then you can go from second order in PSO to first order by doing a zero inertia limits. And so you can basically have the whole pipeline of how you get from the PSO to CBO. There's also a whole sequence of papers, mainly led by Lorenzo Paresci. Okay, then this idea of including memory, which in the PSO is done by looking at the personal best, is also a way of actually addressing the curse of dimensionality. Because in some sense, if I evolve a given number of particles, but then I also consider all the previous positions where these particles have been, it's as if I'm increasing my number of particles without extra cost, where you have to save in memory bits. Okay, and then their version was like truncated noise. And also this paper I find quite exciting, where CBO was implemented for federated learning. And then there's applications in finance and event estimation and so on. So it's starting to gain some traction. Okay, so I've been talking a lot about what we can do at the PDE level thanks to the mean field limits. So let me just tell you what are the results that are known so far. So this would be the mean field particle evolution, so like the evolution of a typical particle. And you see it's exactly the same equation like what we had for the algorithm, just that I'm replacing in the m beta the empirical measure with the law of particle bar theta. And then the corresponding Fokker-Planck equation is this one. And you see it's a nonlinear and non-local model. And it's posing some challenges for the analysis because in this weighted mean, you have to renormalize. And so you have to deal with that. Okay, so this is a convergence result for CBO on the mean field level, where you get exponential convergence in Wasserstein distance. But you see that, so here this is the Dirac sitting on the global minimizer, right? But you see that this is only true on a finite time interval. So you're not actually getting all the way to the Dirac that you want to get to in terms of the guarantee that you get. But if you take your beta large enough, you can take this time interval as large as you want and therefore get closer to your global minimizer. So what this is basically saying is that you can guarantee to collapse to a point that is as close as you want to the global optimizer, as long as you take your beta large enough. That's what this is basically saying. And the proof strategy for all the different versions of this result that exist always follow the same idea. They always go in two steps. So the first step is that you prove consensus formation. And that's actually why this is called consensus-based optimization, because what you show is that your particles, they always collapse to a point. And that point is the consensus point. So for this part of the proof, you're not asking the question whether this consensus point is a good point. Like this might be far away from the global optimizer, right? So, but what is clear is that this point is going to depend on beta. So you're fixing your beta, you're sending time to infinity, and you prove that all your particles collapse, right? And then the second step is to show that this consensus point is as close as you want to your global optimizer by taking beta large enough. And that's basically just Laplace's method. So that's sort of the key ingredients behind all of these proofs.
Franca?
Yeah.
Sorry to interrupt. May I ask this question? I'll try to speak a little bit louder. So are you saying that the first equation there has some sort of a limiting measure?
This one?
The first one.
Yeah, it should be the Dirac sitting on a consensus point. Yeah, sitting on this point. So sorry, I will repeat so that the people online can understand. So the question is whether this mean field SDE has a limiting measure, right? Yes. So the limiting measure is a Dirac that sits on some point, which is the consensus point. And then you still have to show that that's a point close to where you are.
And what are the conditions for that?
So you have some conditions on your initial data, and you also have some conditions on your noise, on the sigma. So if you take your sigma too large, then you cannot guarantee the convergence. Yes. And I mean, the initial condition has to be spread enough. So if you initialize all your particles very far away from your global optimizer, and practically speaking, you also have to take your beta not too large at the beginning, because if you do that, then your particles will collapse in the wrong well. So I will get to that later, but there are some practical issues of if you actually choose your beta adaptively. So if you choose your beta small at the beginning, it helps you to prevent collapsing in the wrong well. And then you want large beta to have to end up at the point that is closer to the global optimum, and also actually to improve the rate of convergence. And so in practice, people take adaptive beta, and that is shown to improve quite well how the algorithm works, but we don't have any proofs for that yet. Actually, Nico did some proofs in his master thesis for just the Gaussian case, and could show that in that case, you can see how, well, anyways, that was for CBS. I will get to that later, but yeah. But please, more questions if there are any. Yeah, I'm happy to give some more context. Okay.
So can you be a
yeah.
little bit more heuristic on why you have like this convergence? Why you have like this consensus? Is due to the fact that the structure you consider is like some sort of mirror version with respect to some it's not obvious to me like to understand why you have like this step one. Why this step one is easy to solve it.
That's a bit the magic of the method. I mean, it's obviously not magic, but fundamentally, I think the reasons why it works is similar to why simulated annealing works. Like you just have this competition between well, exploration and exploitation, right? Which on the one hand appears in your drift term, which makes particles collapse, and then in your noise term, which makes particles explore. But now here you have another knob for tuning the exploration-exploitation trade-off, which is the beta, the inverse temperature. And so you can use both of them. So that's why you need the noise not to be too large in order to be able to have convergence. And the first proof for the convergence was done by just basically looking at the time derivative of the variance of the mean field model and then showing that that decays. And then you can also do an argument for the Wasserstein metric. So you can directly look at the evolution of the Wasserstein metric between like your initial measure and either the Dirac on the global consensus point or, sorry, the consensus point or the Dirac on the global optimizer. I mean, both proofs you can do. And then the gap is just a Laplace method in the end. Yeah, if you look at the computations, I think it will come up, yeah.
One small question related to that. So this M beta is some sort of mean.
It's a weighted mean, yes. So yeah,
That's why the,
if I go back here, that's the M beta, yeah.
and is that why intuitively it's just converging to some sort of mean, so it collapses on something?
Yes, that's right. So let's say if I take the beta equal to 0, right? Then you look at this weight and it just gives you 1/n. So if I take beta equal to 0, I have the normal mean, which means that I give the same weights to all of the particles. So this is giving more weights to particles that are in a beta location. And if I take beta to infinity, I put all the weights on the particle with the lowest energy and no weight on the particles that have not the best energy. So that's basically the idea of this weighted mean. Yeah. Yeah.
So for the convergence guarantee that you have, is there an estimate for that lambda?
Yes, there is an explicit formula actually. I didn't put it, but the lambda is absolutely explicit. It depends like on the dimension, on the sigma, on the beta, on everything. Yes.
If F is convex, it's fully convex, is that lambda also nice?
Yes. Yes. Okay. Yeah. And yeah, so the lambda also depends on the objective function. So you have, depending on different versions of the proofs, you have like local Lipschitz assumptions, for instance, on your objective function, and then that constant will also show up in the rates. You have, yeah, there's a whole list of assumptions. I have them in the appendix if you want, I can pull them up, but yeah. I didn't want to get too complicated here, so I didn't put the details. Okay, so this is just to tell you sort of the high level philosophy, right? Like everything I just shown you is basically here. So continuous time, PDE, like mean field level, but the actual algorithm obviously uses discrete time particles. So you have these two steps, right? Like you take a limit of your time step going to 0, and then you take number of particles to infinity. And if you want to translate what we know in terms of guarantees from here to the actual algorithm, there is still a lot of work to do, actually. And this is also something that we're working on currently. But let me first tell you sort of at least how you can stitch together like this gap, first of all. So like what if you want to now prove convergence for the actual particle algorithm, so finite number of particles. So first of all, you can do just use triangle inequality, compare the particle algorithm to the mean fields evolution, and then the mean field evolution to where you actually want to go. So this is the result that I just showed you. So this part we know how to control. So then, of course, we want to show the mean field limit and control this part and have a rate in as the number of particles go to infinity for this to go to 0. So there are several results already in the literature about mean field limits for CBO. The first proof that appeared used a compactness argument, which basically means that you have no rates. So you have no control in terms of the number of particles, right? And then this was a result by Massimo Fonazier, Tim Klock, and Konstantin Riedl, who worked on this at the same time as like Nico worked on the mean field limit proof when he was doing his master's thesis. And their strategy is also quite similar, but I think there's one key ingredient that we were able to prove that removes their formulation where you have to do everything on some set omega epsilon for your probability events, where you assume that, okay, everything outside the set is small, and then if you condition on that set, you get your convergence. But this constant blows up as you take your epsilon to 0. So what we would really like is to estimate this guy with a uniform constant with an explicit rate in the number of particles, right? That's the goal. And one classical approach for this is Schnitzmann's argument. If you have ever done anything in mean field limits, like you will know about Schnitzmann's argument, which is a coupling approach. So you take your particle algorithm, and then you compare with the corresponding mean field SDE with the same noise. So that's why coupling argument, right? Because you couple the noise. And in the classical Schnitzmann arguments, you need to have your functions, like for the drift and for the diffusion, to be Lipschitz in certain ways. And that's not the case for CDO. And this is why you can't just apply Schnitzmann's argument out of the box. Because this M beta, even just by itself, this weighted mean, is not Lipschitz. It's not globally Lipschitz. But it's locally Lipschitz in some nice ways. And this is why actually you can use a coupling argument in the end to make this work. Okay, so here I did put some assumptions on the F in the end. So for this finite time mean field limits to work, you need some like growth assumptions on the F. Actually, these can be relaxed. So in the paper, we have sort of a more general family of assumptions. And then those different assumptions on the objective function turn up in the rate. But I think for most cases, this is probably fine. So I decided to put sort of a more easily digestible version here. But so you have some Lipschitz, some local Lipschitz continuity, and you have some growth condition at infinity. And then you can show this finite time mean field limit result. So this is for any WP distance in the end. And so if I take the P on the other side, if I do 1 over P here, then the rate is like 1 over square root of number of particles, which is sort of the classical mean field limit rate that you would expect also from a lot of other models. Okay, so I don't know how much time I have because maybe I will, oh wow, already later than I thought. Okay, so I will skip a little bit the proof, but I think I just want to highlight this part because this is basically saying that the weighted mean is locally Lipschitz continuous, but only on a restricted set of measures. So you can allow yourself to take any measure with Pith moment bounded, but then for the other measure, you need to have a uniform bound for the moments. And the nice thing is that we do have moment control on the mean field level. We don't have moment control for the particle system. And so what we can do is for this guy, we're choosing the mean fields measure for which we do have this control. And for this guy, we choose the particle measure. Okay, I will skip the rest of this. It's using stopping times as a technique. And maybe let me just quickly mention a little bit about sampling. So the idea was to take the CBO and try to turn it into sampling algorithm by sort of adding noise in a way that you prevent the particle collapse. And you can do that in many ways. And so we started actually with a quite general family of finite time particle methods where we put some parameters and then we ask, okay, what parameters do we want to choose so that everything works out? And so you see here that we're putting a C beta. So the C beta is a weighted covariance matrix, which is just taking like as the same way as you have the weighted mean, basically. And so then the question is, for which choices of alpha, beta, and gamma do we get e to the minus f as the steady state of the system? And it's always easier to look at Gaussians first. So let's assume that our target is Gaussian with mean little a and covariance big A. And then you compute the weighted mean is also A, and the weighted covariance is given like that. And then you can say, okay, if at time n, I am at this Gaussian, and I want that in the next step, I'm still at the same Gaussian. So if I'm asking, am I at a steady state? then that gives you a condition. And so that tells you actually what the gamma should be. So this tells you like how you want to, okay, so the gamma is what's in here, right? And you see that it actually grows with beta. And we want beta to be large because we want to use the Laplace principle. And so what this tells you is that as I take beta large or beta to infinity, I'm actually blowing up the covariance. And that's what prevents the particle collapse. Okay. And then we also have rates. I mean, if the target is Gaussian, this is quite explicit. I mean, you can, Gaussians remain Gaussians. You can write just a system for the moments, and then you can prove convergence for that, and you can find explicit rates. Okay, but the question is obviously like, what if the target is not Gaussian, right? But before I go there, just to say that you can obviously also write down the time continuous version of this. And you can think of this alpha parameter that I didn't comment yet on as being a kind of time step size. So you can think of this alpha as being e to the minus delta t, where this is your time step. And so as you take delta t to 0, you're taking the alpha to 1. So you can take your alpha between 0 and 1, and going to 1 is basically the continuous time case. But you see that when it also shows up in the rate, and you actually want the alpha to be 0. I mean, that gives you the faster rates. Okay, so that gives you continuous time sampling method, and we can analyze that. And in fact, we have a theorem where, if you think about Gaussian targets again, then you get an exponential rate of convergence. Okay, but what about non-Gaussian targets? I mean, that's what we're really interested in. So the first thing is to note that this dynamic propagates Gaussians, even if the target is not Gaussian. And also, if you write down what is the condition for the steady state that the steady state has to satisfy, it's this equation, which tells you that the steady state is always a Gaussian. But it's not clear in general what that Gaussian is, because it's not easy to solve this equation. But it's a Gaussian, which basically means that this way of doing sampling will not recover the e to the minus f if your target is not Gaussian. It always gives you a Gaussian approximation. And the Gaussian approximation is exactly the Laplace approximation. So if you have something that is very multimodal, then this is not the way to go, right? Although there are adaptations of CBO for multimodal targets. And I think it would be interesting to see whether we can use that to actually adapt CBS for sampling from like multimodal distributions, but we haven't done that yet. And then we also have convergence result in the non-Gaussian case, but you actually need to use like higher order expansions in Laplace's method. It becomes very cumbersome if you're in higher dimensions. So we wrote it down in 1D only, but I think like fundamentally there shouldn't be any restriction for the same result to hold in higher dimensions. But yeah, you basically show that this mean and covariance of the target of your method, or the like long-time asymptotics of your method, are close to the mean and covariance of your Laplace approximation of your targets of order 1 over beta. Yeah. Okay. I think I will skip this. You can also use the CBS for optimization, but I don't recommend you to do that because CBO is better at that. Okay, so let me maybe just escape, and I guess I would have to share my whole screen. Yeah, let me share the full screen, and then no, I don't see anything. Okay. Let me just show you some numerics. Okay, so there's sort of 3 examples I want to show you. This one is a toy model that you will find in many papers that suggests sampling methods, and it's sort of a benchmark problem. It's a 1D boundary value problem where you don't know the diffusion coefficient and you don't know one of the boundary conditions, and it's a nonlinear target, so it's a nonlinear inverse problem. And you look at 2 locations, x1, x2, to the solution of this problem, and you add noise at your value of the solution there, and then you try to recover the values there. So this is what the contour plot looks like. And then I will also show you, these are again like typical optimization functions that you want to test your stuff on, Rastergen and Ackley functions, because they have many, many local minimizers. It's kind of an eggshell type situation, and one global optimizer. And so I just want to show you how that looks like in practice. So I don't have too many tabs here. Okay, so this is the elliptic boundary value problem. So the black cross is the global optimum, and the red cross is the weighted mean. And so then you see you have your particles, and then how fat they're printed says what is their weight relative in the sum. And so you see that they don't collapse, but like all the particles go where most of the mass of the measure is. And you can also see that it has a bit of a banana shape because it's a nonlinear problem, but this is basically a linear approximation. So like a Gaussian approximation of this, the way how the particles end up. Okay, so here we have the Ugly function. And so here we're actually doing this adaptive beta. So you see how the beta increases. And currently there's no rule how to increase beta. So this is also an open question. The way we did it here is using effective sample size, which basically says I fix that roughly half my particles meaningfully contribute to the weighted mean, and I choose the beta in function of that. And so you would expect that as your particles sort of find the good region and collapse, that more and more particles contribute to the weighted mean. And so that drives your beta up, and you can actually see that happening. So we're not hard coding that the beta should increase, but this is what's happening. So maybe I just play it again, and I don't know if you can see that, it's very small, but so effective sample size is roughly a half, a little bit less than a half. That's what we fixed it to. And the beta, yeah, starts from 0 point something, and then now it's already at like, yeah, it's increasing very quickly. Anyway, and then we have estrogen, same thing. So yeah, I mean, this is for CB, well, this is for CBS now, yeah. Okay, maybe I go back to, go back to full screen. Here we go. Okay, so there's some new exciting developments because so we had in, when was this? 2023 in March. We had a conference where we tried to get all the people together that work on CBO and related methods and also ensemble common methods. And like one thing that really came out of this workshop was that there's a gap between people who want to use these algorithms and people that actually know about them and work on them. I mean, for CBO, because it was very new. So we got together a group of people that focus on software implementations. And since March this year, we have now 2 packages available on GitHub. So in Python and in Julia, and not all the variants are available yet, but it's evolving. So if you're interested, you can get involved. This is the GitHub. And then there's also under the leadership of Xi Jin, who runs a big group in Shanghai. They just published a new software that is based on random batch approaches for molecular dynamics that are highly scalable. So this came out in June, so just last month. They have a free version, but there's also, you have to pay for the more advanced versions, but there's also GitHub that you can look at, and they also use CBO approaches as part of that machinery now. Okay, so that's exciting software developments on that front. And yeah, maybe let me just summarize. So this was for CBS, I think. For Gaussian targets, you have very nice exponential convergence results, and the results are better when beta is larger and alpha is smaller. And then for non-Gaussian targets, we need to have this assumption here. So you need a uniform upper and lower bound on the Hessian. And just some comment on that. I mean, when we proposed the ensemble common sampler, which is sort of using a similar idea of preventing particle collapse to turn an optimization algorithm into a sampling algorithm, we were hoping that thanks to the gradient flow structure of the ensemble common sampler, we would be able to show convergence results for a larger class of targets. And that did not turn out to be true. So still currently, the only setting in which we can show any convergence for the ensemble common sampler is when your target is a Gaussian. Very frustrating for me because it's something I would really like to push beyond the Gaussian setting. And so it was really nice that in the CBS, even though we don't have any gradient flow structure, you can go, like you can get a convergence proof for just having upper and lower bound on the Hessian, which is generally sort of the best you can hope for, I think, for these kind of proofs in this business. Okay, this is just sort of repeating what I said before. I think, let me conclude. So in terms of perspective, something that we're working on right now is uniforming time mean field limits for CBO. Because when you think about this whole pipeline, right, like if you want to actually translate results on the mean field level down to the algorithms, the problem is that you want to use the T to infinity results, but then you only have finite time mean field limits, right? So if you can get uniforming time mean field limits, that would be really nice. And we're about to finish a result on this, but so hopefully this will be on archive soon. So maybe as soon as we typed it up, we just proved this last week, so I'm very excited about it. But we're getting the uniform in time at the expense of getting roots. And of course, that's, you know, a trade-off. I think the holy grail would be both, but I think that's very hard. And then there's also the question how to go from the discrete time to the continuous time. And there's the same issue, like if you think of the like classical proofs, like, okay, Euler discretization, whatever discretization you use, converges as delta t goes to 0. It's always on a finite time interval, right? So if you want to have the full pipeline, you also need uniform in time transitions for that. And we think we also got that down now. So we sort of practiced on a different model, which comes like from the Cocos-Mail literature, and we managed to get it to work there. And so now we should be able to also apply it to this one. So our goal is to kind of have the full pipeline to connect the actual algorithms to the PDE models. Yeah, and then there's the story of the adaptive beta that I already mentioned, and software implementations. Yeah, so I think I will just finish here. I think my time is up. I'm happy to finish.
Very exciting results, and thank you for highlighting the open questions in this direction. Questions? Would you like the microphone, or would you like to speak louder?
I can speak louder. So we did some a few years ago. We did some work on SMC. I got into the continuous time of SMC for optimization, and there we got a grade that was number of particles to the d. Do you think something like this happens here? Like number of particles need to scale exponentially with dimension, or is it actually better?
So which rate do you mean? Do you mean the mean field limit rate, or do you mean the time to infinity rate?
No, I mean in a finite particle setting, if the dimension of the optimization function grows, do you think the number of particles should grow exponentially?
Yes, I mean, this whole setup of algorithm does not get around the curse of dimensionality. Like with tricks, you can get rid of the dimension dependence in the rate of convergence as time goes to infinity. But I think you're still in a situation that if you don't have enough particles to explore properly and to see like where your global minimizer is, then you have no chance. So yeah, I think overcoming the curse of dimensionality in that sense, like how many particles you need in order to have some guarantees to find the global optimum, that's still open, yeah. If you have ideas, I'm curious.
Next question.
Thank you. Very nice talk. I guess two questions. One, do you know a way, is it possible to change CBS to converge to the correct target, e to the minus f?
So what, to multiple targets?
To the correct target, e to the minus f instead of the Gaussian.
I don't think CBS is able to do that because the fundamental way the algorithm works is using the Laplace method, which drives the whole dynamics to the Laplace approximation, which is always a Gaussian. So I think if, I mean, the only way that I can see how you can use this when you really care about something that is non-Gaussian as a target is when you use the ideas that, like from polarized CBO that Leon Bungert introduced for the CBO, where you have like multimodal targets and can turn that into sampling algorithm that you sort of prevent particle lapse in each of the wells. Like that could be an idea, but there's nothing at the moment on that. So yeah.
Okay, thank you. And I guess I was wondering, do you have an estimate? Is there an estimate of the Gaussian limit to the true target for CBS
Yes. So I mean, if the target is Gaussian or if the target is non-Gaussian.
for non-Gaussian?
Yes, that was I mean, only in 1D do we have the convergence rate currently in the paper, but I believe that it should also work for higher dimensions. Like this was this result. So you basically so what we allowed ourselves to do, so this is for non-Gaussian targets, but even if you have a non-Gaussian target, you can allow yourself to choose Gaussian as your initial condition, because you know you will only get a Gaussian in the limit anyways. Then you know that you will stay Gaussian along the way. So your M of t and C of t is your meaning covariance at time t, like in the case of a non-Gaussian e to the minus f, right? And then you can show that those converge to some limiting value. And then you want to show that that limiting value is close to your global minimizer and the inverse of the Hessian of the target evaluated at the global minimizer as beta goes to infinity. And we can do that with an explicit rate. So I summarized here, but we have like the explicit expression. And the sort of the technicality here is that in order to prove that, you actually have to go to higher order terms in the Laplace, like in the Laplace method. And this just gets very tedious, but yeah, it's all explicit and doable. Was that your question?
Yeah. I guess I was wondering about KL divergence or instead of comparing covariance.
Yeah, that would be interesting. We didn't look at any rate in KL divergence. Yeah.
Thank you.
Any other questions?
Maybe a very short one. What would be typical values for beta or the number of particles that people use?
I think in the simulation you saw, I mean, technically you want your beta as large as possible. I mean, when you choose it adaptively, you will easily end up in the thousands. Yeah. There's another trick, by the way, that people do in practice for PSO, and I think for CBO that could also be good. They reduce the number of particles. So back to your question about like the curse of dimensionality, like in practice to address that, what people do is they take a huge number of particles at the beginning. And so then once the particles sort of move towards a region, you allow yourself to kill particles along the way. And then the more you have the collapse, the less particles you need, and then it becomes computationally cheaper. So all these like tricks of increasing the beta dynamically with some rule that is totally arbitrary and at the moment, no proofs, and the same for like, how do you kill particles and how quickly, there's no proofs on this at all. And I would be really nice to have some proofs. So again, if anybody has ideas, I would be very happy to chat.
Okay, great. Thank you very much again, Franca.